Hey everyone. So I am doing um, covering hypothesis testing um, between populations, specifically difference between two population means. Um, so yeah, let's get started. Um, so hypothesis testing for two population means can be thought of as an extension of the test for one population mean. Um, Individual populations will have their own sample mean distribution and comparison, therefore, of the populations will also be a random variable. So I made some populations in R. So you found a way to create matrices that are full of randomly constructed values. However, they have a predetermined mean and standard deviation, which was helpful for kind of validating the idea that if x is a random variable, and I'm sorry, the mean distribution of x is a random variable, and y, the mean distribution of y, is a random variable, then the difference between the mean x and mean y is also a random variable. So if we're just looking at this to kind of review some concepts, if we take a random variable or random sample like that, that's going to have a mean, and that's going to be different than taking a random variable, or I'm sorry, a random sample, something like that. When you take a different sample, you're going to have a different mean from it. And this is all the same logic. It also applies to uh, multiple populations. So independently, obviously, you take a sample and find the mean. Um, you're going to have the same dynamic regardless of the fact that there's one or two populations. So next, I went through and set up a simulation. So this shows a sample mean distribution for the previous populations from the prior slide. The mean is determined from a sample size of 30 um, from the different populations above, and this sampling and then computing the mean was performed 1,000 times on each population, and then we got these frequency distributions of the means for the samples taken from the different populations. And what's cool about this, at least to me, was that I knew because of setting up the parameters that sorry, the actual population mean was 16, and what this showed here, what is that? It's probably like 16.2. Was the simulation came up with as the population mean from the sample. So that's very close, and in this case, it was actually dead on for population Y. And of course, if you run the simulations again, you're going to get different values. But consistently, it was always very um, close to the population. Nope, sorry, getting ahead. So I did a similar simulation for the distribution just to kind of demonstrate that the difference is also a random variable, and the same mechanisms apply that we've been using before, and the simulation demonstrates that as well. Um, so here the sample consisted of a set comprised of differences between randomly selected values from each population. So I took a random value from X that was randomly selected. I took a value that was randomly selected from Y. I found their difference, and that difference became part of the sample. And then I did that until there was 30 of them. So I took, I had a sample size of 30. I found the mean of that. And then I saved that mean, and I did that 30 or 1,000 times like I did before, and then got a distribution, a frequency distribution like this. And I think what's cool about this, what it demonstrated is that, we had a mean of 45 for Y and a mean of 16 for X, and the difference between those was 29. And so, we're seeing again that, the same statistical principles hold true, allowing us to use a lot of the same mechanisms that we used in the past. Cool. So in reality, though, populations are not typically encapsulated by data, and when they are, we don't really need hypothesis testing. If we are working with a closed population and we have all the values, we could just figure out what the mean is. We don't need to do a test to see, if a new sample will demonstrate an updated expectation for what the mean is. But instead, in reality, we're working with samples whose means are going to be the sample mean is going to be essentially a value of one sample. We're going to have a sample from X and a sample from Y, and we're going to work with that as kind of an extension of what we've already been doing. Therefore, the techniques that were deployed earlier are deployed here. We can't count on, the reason being that we can't count on either of the samples being exceptional representations of the population. It can be. We could be taking, a value from the middle that's the highest likelihood in terms of a sample, but there's nothing to say that our sample can't be coming from here. So it would be, we would end up with a mean of 15.7. And because there's not that fidelity, when we're sampling, we're going to have to establish significance. So we have to be able to show that any discrepancy between the null and the test statistic derived from the samples must be beyond a certain threshold to avoid the discrepancy being explainable by stochastic events that are built into the data collection process, either intentionally, I'm using pseudo random sampling for this, so it's intentionally meant to be random samples. It's fundamental that be there, otherwise we can't make the assumptions that we're making, or it can be just noise from if you're doing like an experiment and you're using the thing that comes to mind, because it's kind of what my focus is doing DNA sequencing. It's lots of accuracy issues. It's lots and lots of data, and not all of it is clean data, so that it ends up with a lot of noise. And you have to make sure that the differences that you're seeing are beyond the to a reasonable degree. We can assume that it's beyond what would be expected if the difference was just randomly generated. So why compare populations? Just to kind of explore that idea, rather than thinking of these sets as populations, which here I want to think of them more as samples from populations. So in these situations, we're looking to do, we're looking to compare populations to determine if like change occurs. So an example would be if if we considered this like an old cement formula, and this is a sample from that population, and then there was a new addition to the formula that they thought would make it stronger, and this is the new formula sample. So the idea being that by comparing the samples, we get a sense of how the populations themselves differ, or if they differ, if it made any difference at all. So that's the kind of thing that we're looking at here. And I updated the green values to just make it a little bit more interesting, because before the mean was glaringly different. Here the mean is much closer and there's much more variation built into it. So kind of like lends itself to the idea that this just being a sample in this instance, we're going to have to deploy the techniques used before, and we're going to have to define the parameters that we've used before. We're just going to use slightly different mathematical expressions to achieve those definitions of the parameters. Alright, so assumptions for population differences for z-tests. Again, this is very much in par with what we've been looking at. N is large enough to validate the central limit theorem being used, negating the relevancy of the population distribution's shape. So it doesn't matter if it's Poisson or uniform or exponential or whatever. If n is large enough, and our standard is 40, and that still applies here. If they're both large enough, then we're fine. We can use the normal distribution and use z-tests. If n is not large enough, we could still use the z-test, provided that the population standard deviations are known and the population shapes are normal. Again, it's not a really realistic situation, because we're not looking at knowing the population standard deviation, because you'd also know the mean. I don't know, maybe there's ways to do it that I'm not aware of, but this would all kind of be not relevant anymore. But the new assumption here is that populations being tested are independent. So, if the populations are independent, then the samples that you draw from them are going to be independent of each other too. So that's another assumption. Okay, so looking at the parameters that we need to use, again, we're still defining standard deviation and mean and test statistic, but the definitions are a little bit different. The standard deviation, the mean, starting with the mean kind of in the middle, maybe we should put it at the top, but the mean is essentially just the difference between the means of the samples, ideally the population, but we'll be using the samples to estimate that. And then, the standard deviation here, we see that we're adding it together, and again, that just reflects the fact that standard deviation is a measure of variation, and it wouldn't make sense to say that anything has negative variation, so we wouldn't have terms that would be defined as negative values. And then the test statistic is very similar to what we've looked at before. We have, kind of what equates to a point estimator when we're looking at confidence intervals. So we have that value, and then we have our null value. our assumption about what the difference would be in this case, that we're subtracting from it. And then here again, on the bottom, we have a standard error value, and this is, the fact that it's summed together again is reflective of the fact that this is variation, so we're not looking at negative values. And then when you're looking at the samples, when the sample size is large, and the standard deviation is unknown, it's essentially, we get to apply the central limit theorem, and therefore we're just swapping out what would be the population standard deviation, and swapping in what is the sample standard deviation. Alright, so this is the data that's needed to make conclusions. In a nutshell, this comes from the textbook. So it gives you an understanding of what the null is. Again, we're looking at a difference here, difference between the mean, and that's simplified as the delta naught. You can see that delta naught come up in the test statistic value, and then you can see the standard error at the bottom as well. The p-value determinations are pretty much the same as you would do for alternative hypothesis in one population test. So again, no ideas, but very much similar to what happens with a lot of the statistics stuff, where we're just adding more stuff, and because everything looks the same, it's very, the biggest potential error is substituting the wrong thing, probably. And then the book also goes over confidence intervals, and again, we're looking at something very familiar where, this is our point estimator that we're building the confidence interval around. Right here, we're looking at our critical value, and at least that's kind of how I think of it, because it looks the same as when you're building, when you're defining what values your test statistic needs to be bigger than. So anyway, and then the last one is the standard error that ends up being a factor of the critical value, and that together makes our confidence interval, which, again, when you look at it abstractly like that, is just the same thing that we've been looking at. Alright, so here we're looking at a problem where we're comparing the heights of white women at different ages, different age groups. So 20 to 39, and then the other age group is 60 and older. Sample sizes are large, so we're going to be able to use a normal distribution for this, even though we don't have population standard error. I don't think it's meant to be interpreted that way. And we have means. So the first thing that it's asking us to do is to calculate and interpret a confidence interval at a confidence level of approximately 95% for the difference between the population mean height for the younger women and for that of the older women. So we're looking for a confidence interval that expresses range around our point estimator, and our point estimator being the difference between the height of younger women and older women. Alright, so I'm not sure how that happened, but this is what we're looking for. So anyway, to build the confidence interval, hopefully I can do this without messing up my recording. Yeah, we're doing alright. We're working with the sample mean, values there, so that's going to give us our point estimator. We got 6.49 minus, or 63, 64.9 minus 63.1, and then because this is 95% confidence interval, our critical value of 1.96 is used, and then we're defining our standard error values here. So we have 0.9, and that's coming from that last column, the top value. We're squaring that plus, so this is pretty much just a distance formula. Okay, so that's our expression. That's what we're doing for A, and that simplifies to 1.52 and 2.08. So that would be the difference, assumed difference between the 20 through 39 group and the 60-year-old group, where the expectation is that the 20 through 39 group will be 1.5 inches taller to 2.08 inches taller than the group that's 60 and older. Alright, so going back and looking again, part B, we're looking at figuring out, we're interpreting our null hypothesis, and we're carrying out the test at a significance level of 0.001. Okay, so we're letting mu1 be the 20 through 39 age group, and mu2 be the 60 and older. So we have null hypothesis of the 39 group minus the mean of the 39 group minus the mean of the 60 and older group, is that being equal to 1, meaning that the assumption is that the 20 through 39 group, it will have an average of 1 inch on the 60 and older group. And the alternative is this difference being greater than 1, and that's weird. Sorry, I'm not sure how to interpret that, but anyway, so with sorry, I was confused by whether or not that was a period or a decimal point, but I think it's just a period, and then that makes the other sentence a little weird. But anyway, with that in mind, this is a one-tailed test, and this is an upper tail test. All right, so the first thing that we need to do then, after kind of interpreting that, is we need to figure out what our test statistic is. So Z is going to give us our difference in mean, which simplifies, that's this thing right here, that simplifies to 8.1 minus 1, so that just ends up being 0.8, and then we're dealing with that standard error again. And that simplifies to 5.63, roughly. Alright, so figuring out what we're working with here, we have our test statistic, and then from there we would calculate our p-value. So I think that's the next, so it wants us to, okay, so kind of looking at C, we're going to figure out the p-value that we should have in B, and then figure out whether or not we reject the null or fail to reject the null. So C, our p-value is going to be P of Z is greater than or equal to 5.63, which is equal to which is equal to 1 minus phi, if we're using our tables, 6.3, which is roughly, that 1, and that from the table, the value that you get is roughly 1 as well, so we're looking at roughly 0, which based on what we our threshold is, 0 is less than, which is less than 0.001. So based on that, we can reject is rejected. So there you go, null. Alright, so anyway, yeah. So then we can therefore assume that the actual difference between the different age groups is would indicate that the 20 through 39-year-olds have more than an inch difference on average than the 60 and older white females. Alright, so the book covers some cautions on observational studies. Observational studies occur when the entities that produce the data are not assigned to different conditions. Just want to make sure I was going there. Condition groups by the investigators. And that happens in a couple of different situations. Sometimes in testing you don't have, it doesn't make sense to do a controlled experiment. Like you couldn't do experiments where you have people crash cars to figure out what happens, and how frequently there's a spinal injury or something like that. That would obviously be problematic. So in those situations, you are using data that's collected from actual people who are injured. And the problem with this is that often we can't account for confounding variables when we're not doing controlled experiments. So when we're doing those types of things that, and this comes up in when we're doing comparisons of populations, you have to be careful essentially with the conclusions that you draw, because we don't know if those conclusions might indicate that there's a significant difference, but we don't necessarily know that it's not due to some other variable that's not really made explicit. Alright, so moving on to t-distributions and t-tests for population differences. So like before, the fundamental difference between Z and T distribution tests is that the population standard deviation is not known, and the sample size is too small. So what I'm doing here is essentially taking the assumptions that I had for Z and kind of clarifying by crossing out, and is not large, obviously, and the standard deviation for the population is not known. But what remains that we, especially because we're not working at large sample sizes, we have to know, or we have to assume that the shape of the distribution of the population is normal. And then again, the new assumption that the populations being tested are independent is also relevant to t-tests as well. The normality is something that can be tested, and you can use quantile plots in statistics software to do that. R has one that is called QQ norm, which is pretty easy to navigate. The logic is that it plots. It's a bivariate plot where it takes the quantile value of each uh, value that you have in your sample, and it assigns it a theoretical, if it is normally distributed, it would be in this quantile, and if it was, and then it determines its actual quantile value based on the distribution of the sample. And if it is normal, then you're going to see a linear pattern, come up in the plots, and the sample values, and when it's plotted, yeah, you're going to see a line. So it doesn't need to be perfect, but it should be close. And if that's the case, then you have validation that the assumption of normality is valid, accurate. All right, so looking at t-test parameters and the test statistic, we're extending from what we've already done with normal distribution, looking at literally the same expressions, and the mean and standard deviation are the same, as when the population standard deviation is not known. And the only difference is that we're denoting the test statistic as t instead of z, even though we're using the same information to derive it, simply because z is, would be a value in the standard normal distribution, and t is coming from t student distribution. So you have to make that distinction. That's an implication of the small sample size and not having the population standard deviation. Another fundamental implication, as before with the t-distribution, is the degrees of freedom. But unlike the straightforward calculation that you got to do with one population, where it's just one less than the sample size, we get a slightly more complex calculation for degrees of freedom when finding the difference between two population means. When you simplify this, typically, unless you get a whole number, which I imagine is very rare, you find the floor, you round it down. I'm not exactly sure why, but that is what you do. So if it was like 15.9, it would still be 15 and not 16. All right, so as before, the book gives you some summative information, the different information that you would use to conduct the t-tests, provides the information about the confidence interval. And again, we're looking at a very, if we look at this very abstractly, we're looking at a very consistent definition for the confidence interval. This would be our point estimator that we're building the confidence interval around. This is our standard error, and this is our critical value based on what we're making the confidence, the significance that we're giving the confidence interval. So again, the idea with the confidence interval being that if you have a value outside of it, then that's significantly different than your point estimator, and you can use that information to validate the idea that you could reject a null hypothesis. One-sided confidence bound can be calculated as described earlier. Same idea that we don't have alpha half, we're using alpha, and it would be a plus or a minus instead of both. The test statistic is what we just looked at, and the implications of the different alternative hypothesis options are the same for p-value determination. Alright, so looking at, let's make sure everything's good with my recording. Everything's good with my recording. Here we go. So now we're looking at, this is not my first time through, guys. We're looking at problem 18 from the book. It's 9.2. That section, the problem's at the end of the section. And the question is, which way of dispensing champagne, the traditional vertical method or the tilted beer pour method, preserves more of the tiny bubbles that improve flavor and aroma? So information that I don't want to live without. But here we go. The following data was reported in the article on the losses of dissolved CO2 during champagne serving. Here we go. So I'm just doing part A, which kind of restricts our inquiry to just this section of the table right here, because we're only working with the 18 degrees Celsius temperature. And I guess probably a 12 degrees Celsius temperature would have an impact as well. You probably see a difference. There's probably more activity, more volatility with higher temperatures than low. But we're not going to worry about that right now. So we're assuming that the sample distribution is normal, so we don't have to do the Q plot, and we don't have the data to do it. But that is something that I didn't see a problem, but I didn't look too hard. But anyway, so part A, we're carrying out a test at a significance level of 0.01 to decide whether the true average CO2 loss at 18 degrees Celsius for the traditional pour differs from that of the slanted pour. So with this, where am I trying to go here? Where are my notes? Okay, so here it's not giving us the hypothesis, so we got to kind of think through it. So our null hypothesis would be, because it said differs, that usually is like the key word that I found is the thing, would be that our difference we're assuming that it doesn't differ as the null, so our difference between the mean would be 0. And then H, the alternative, is just not 0. Alright, work with me there, pen. Alright, so because this is t distribution, we need to figure out what V is. And that is kind of that ugly expression that I went through before. And then we have this right here. Okay, so that's just plugging in values. Our standard deviations, oops, sorry, not all of them, just those. And our sample sizes. And that's pretty much what we're working with in the bottom. And just the terms are different. Over 4 minus 1 plus all that squared. Oops. Over 4 minus 1. There you go. That's semi-legible. And then we get roughly 4.9 for that, and we have to round this down. So we get 4 for that value. And then our t-test statistic value is just The difference between that minus the null difference. So that is this minus 0, which, you know, kind of just not worry about too much. And then we're dealing with defining our standard error here. 0.3 squared over 4 equals 1.03. Alright, so that's what we're looking at there. I want to see if I can do this. Use those values in R. I think I started this and then I screwed up my recording. The recording's still going, which is great. So, alright, so taking the information from problem 18, we had a t-test statistic of 1.03 and degree of freedom of 4. In R, I'm just looking at using this as a way, this function right here, pt. There's a couple different functions that you can see here. This finds the probability based on a value, a t-value, and that will give you a density function. So for that you need an x value, and this will use probability to give you like a critical value for a t-distribution. Anyway, so, well, you can be a critical value, it could be a different value, but when we do this, I jumped to the punchline. But anyway, when we do this, we get this value for our p value, but in actuality, because do 2 times that value to get an accurate p-value, which gives us 0.361236. That's a nice palindrome. Anyway, so basing that on our alpha value of 0.01, this is a situation where you definitely failed to reject the null, because its p-value is much larger than your alpha value. So yeah, that's it for me, and I will see